This is the AP exam review for Chapter 10 test. We'll take a look at 4 multiple choice AP exam questions, some of which are simpler than others. But here are a few. Number 1, a rigid metal tank contains oxygen gas. By rigid, we mean its volume cannot expand. Which of the following applies to the gas in the tank when additional oxygen is added at constant temperature? This is also important that it happens at constant temperature, which means we're adding it slowly, not allowing the temperature to rise. A says the volume of the gas increases. Now that's not correct because the tank is rigid, and because it's rigid, the volume cannot change. Now the gas particles themselves, remember, we consider that they don't take up any volume on their own. They're so tiny that they don't contribute to the volume of the whole container. Their movement is what causes, you can say, the pressure and the volume. B says the pressure of the gas decreases. This is actually the opposite of what happens. Since you're adding more gas to the vessel, the pressure would increase. So the pressure of the gas decreasing is wrong. Let's take a look at D. D says the total number of gas molecules remains the same. This is not correct. Since we're adding gas molecules, when oxygen is added, we're actually increasing the pressure on the inside, and we're increasing the number of molecules. So that one is out. E is a bit strange. It says the average distance between the gas molecules increases. This is also incorrect because the average distance between gas molecules will decrease as you add more and more and more molecules. So this again is the opposite. The correct answer is the average speed of the molecules remains the same. That's true. Now the reason the speed of the molecules remain the same is because it happens at constant temperature. Remember from the notes that temperature is a measure of how fast the kinetic energy, the average kinetic energy, or how fast the particles are moving. So because temp stays the same, this is why C is true. So think about this. Think through why these are the answers as we go along. Number 2 says a 2-liter container will hold about 4 grams of which of the following gases at 0 degrees Celsius and 1 atmosphere. Now, you could apply a PV&RT problem here and try to solve for moles, and then try to solve for grams, and all 5 of these cases. But I propose a different method, and that is taking account or taking advantage of the fact that 1 mole of a gas takes up 22.4 liters, as we've seen in our lab. And so if you have a 2-liter container, then you have, roughly speaking, about 1/10 of a mole. So we're actually dealing with 0.10 of a mole. Now, a little less than 0.10 because 0.10 would be, 2.2 liters. So really we have a little less than that, we'll say. And so since we have 1/10 of a mole, let's get the molar masses of all these gases and see which one matches about 4 if you divide it by 10, about 1/10 of it. So if you take a look, the molar masses of SO2 would be, you got oxygen is 16 times 2, you got 32. Sulfur is roughly 32. So we have roughly 72 grams per mole for sulfur dioxide. For nitrogen, each nitrogen is about 14. We got 28 grams per mole. Carbon dioxide, if you calculate it, will be about 44 grams per mole. This is butane, C4H8. Each carbon is 12. That gives us 48, plus another 8. That gives us about 56 grams per mole. And nitrogen and hydrogen, about 17. So if you know that these are the molar masses, and you know you have about 1/10 of one of them, which one would match 4 the best? Well, 1/10 of this guy is roughly 4. And because we said that we have a little less than 0.1 of a mole, that would match perfectly. So CO2 is actually the answer. Again, you could have done this by by applying the PV&RT equation, PV equals nRT, and then solving for moles, because they're given temperature, you're given pressure, you're given volume, and then try to convert to mass for each one of these. That could have also been a possibility. Okay, let's take a look at the next 2. And the next one gives us a little figure and some captions to go along with it. The figure above represents 3 sealed 1-liter vessels. Here they are, each containing a different inert gas. Inert because we have argon, neon, and helium, the noble gases, all at 298 Kelvin, which means the temperature is the same in all 3. The pressure of argon in the first vessel is 2 atmospheres, which is labeled for us. The ratio of the numbers of argon, neon, and helium atoms in the vessel is 2 to 1 to 6, respectively. After all the gases are combined in a previously evacuated 2-liter vessel, in here, what is the total pressure of the gases at 298? There's a number of different ways to attack this one. This is a tough one, and they're trying to use conceptual ideas of gases with a little bit of math, some simple math. So the first thing to take advantage of, the fact that it's a 2 to 1 to 6 ratio, this means if they were in the same vessel, we could say, the neon would be 1 atmosphere, and helium would be 6 atmospheres, 6.0 atm. Essentially, that's the reason this happens is because the pressure is directly related to how much you have. This is actually Dalton's law of partial pressures. Remember, the more moles you have, the more pressure you have. It's directly related. That's where we can relate their mole ratio essentially to their pressures. So what we're going to do, let's combine all these pressures together. Dalton's law says you can actually combine them. So if you were to combine all of them into one vessel, so actually we're going to put this one in here and this one in here as well. So into a 1-liter vessel, actually let's just transfer them all into here. In 1-liter vessel, we have 2 atmospheres. Let's just do it like this. We have 2 atm of argon. We have 1 atm of neon, and we have 6 atmospheres of helium. So you can add the pressures together as long as it's in the same 1-liter container, as long as you don't change the volume. Because the more moles you add, the higher will be the pressure. So this container will, by now, have a total of 9 atmospheres of pressure. Our 1-liter container has 9 atmospheres of pressure. And then they're saying we're actually going to move it to a 2-liter container. So effectively, we're doubling the volume. And what happens to the pressure as we double the volume? The pressure gets cut in half. It's an inverse relationship. This is Boyle's law, which says if volume increases, pressure decreases by a proportional amount, which means our pressure gets cut in 2, and we get 4.5. And that would be the answer. So B is actually the correct answer here. So we've used some strange concepts, put them together to figure out the new pressure. Not too bad. Let's attack the last one here. And the last one says gases W and X react in a closed rigid vessel to form gases Y and Z according to the equation above. The initial pressure of W is 120 atm and X is 160 atm. No Y or Z is initially present. The experiment is carried out at constant temperature. What's the partial pressure of Z when the partial pressure of W decreases to 1 atmosphere? So what we're saying is these two gases are placed into a container, and then they react to form these two gases. And we realize that the mole ratios of these is just 1 to 1 to 1 to 1, which means for every W that disappears, we form 1 mole of Y, 1 mole of Z. So by taking a look at how much W went down by, since we began with 1.20 atmospheres of pressure, and we ended up with 1.0 atmospheres of pressure, the difference here is we lost 0.20 atm. Now, for every one of these moles that we lose, we gain one of these moles. That's what the stoichiometry tells us. So it's as simple as saying Z actually has a pressure now of 0.20 atmospheres. And the reason you can do this is because moles, again, are directly related to pressure. The higher the pressure, the higher the moles. And that's why this can work. Okay, so this was a pretty short video to review. A few of these will show up on our test. See you then.